Okay, good afternoon, everyone. And this afternoon, we're going to be discussing the topic of glass. And glass is a frustrating piece of forensic evidence, frustrating piece of physical evidence, because thinking about it, we might think that glass could carry a tremendous amount of information for us. Unfortunately, that is not really the case. It is seldom that glass actually contributes in a major way to investigations. It can, however. And so where glass is involved in a scene, then it has to be carefully examined. But it is very difficult to tease out information, as you'll realize when I describe what glass is and how it functions and everything else. The fact of the matter is glass is incredibly common. And so broken glass in particular features very, very frequently at a crime scene. And the source of that glass is many and varied. So it might be important. For example, let's posit an ideal situation. There has been a break-in into a home. It's just been vandalized and ransacked and everything. And then the suspect has left. The suspect got in through a window by smashing a window. There is broken glass all over the scene. And the suspect sometime later is arrested. And in the cuff of his pants or wherever, he has glass fragments. And when those glass fragments are closely examined, they are large enough that they can be fitted together with glass fragments from the broken window at the scene. Well, that fitting, it gives the glass individual character and is a very, very strong suggestion that this perpetrator actually was the one who broke the window, came through the window, inadvertently collected pieces of broken glass and carried them away somewhere else. But that is an absolutely ideal situation, and it's one which almost never occurs. Broken glass is incredibly common at crime scenes. That is true. Not only if somebody has broken in a window or whatever, that is obvious, but also because scenes of violence, for example, are extremely dynamic scenes. And glass is very common in any household. We have glasses that we drink out of, glass in the windows, etc., etc. And broken glass often results from a struggle, whatever. And if a perpetrator is involved in a scene like that and glass is smashed, it is very likely that they have at least some glass fragments on them. But the difficulty is as follows. First of all, glass is very common. Go into any home and you are likely to find broken glass. So if you're looking at the home of a suspect and you find broken glass, that doesn't necessarily tell you anything, because broken glass is common. There's glass everywhere. Glass breaks the whole time. It is extremely unlikely that this scenario that I told you about, where we managed to fit glass together to show individual character, it's extremely unlikely that that is going to happen. Even if we recover glass from a suspect, it is difficult to tie the glass we recover from the suspect to glass at a scene of a crime. There are very few characteristics in glass which give it individual character. Instead, we have to deal always with class character. And the class characters, in fact, are so common. Glass itself, glass of many different kinds, is so common that even the class characters are unlikely to give us much information. Nonetheless, because glass is involved at crime scenes so often, because broken glass is so often present. And because glass fragments can be recovered very frequently from a suspect, it is essential that the glass be examined in as far as it possibly can to divulge whatever information it can. And there have been cases, certainly, where examination of glass fragments has at least bolstered a circumstantial case, if not broken a case. But they are few and far between. So let's have a look. First of all, let's get it clear in our minds. There are many kinds of glass. Glass is very, very common. And in your own home, you have probably got several kinds of glass that could conceivably be broken. You have probably also in your home got broken glass. It's probably glass shards somewhere in your home. Once a piece of glass breaks, it is very difficult to clean up all of the shards. This is another thing. If a suspect tries to clean up glass, it is very seldom that they will be able to clean up all the glass. If they try to get rid of glass from their clothing, they may only get rid of the large pieces of glass. They do not realize that there are small pieces of glass which carry just about as much information as the larger pieces. Glass can be embedded in clothing. Glass fragments can be embedded in clothing. Glass fragments can be carried away. Glass fragments can even be embedded in tissue of both perpetrator and any victims, for example. So there are two major characteristics of glass which are immediately measured to try and give character to whatever glass the forensic investigator is looking at. The first is the density of the glass. Glass varies in density, usually around about 2.5 grams per milliliter. And get those terms in your head. Grams per milliliter. Density is measured in the metric system. And I'll explain exactly how in a second. So the density of glass is irrespective of the size of the piece that you're looking at. A small fragment has the same density as a large piece recovered. The density is a constant property for that particular piece of glass, and density varies with different types of glass. So there's at least one characteristic that we can look at to maybe compare our questioned piece of glass with some other sort of standard. Let's try to think, okay, we've recovered a little fragment of glass from a suspect, and we're trying to tie it to glass which was broken at the scene of a crime. So the first thing we're going to do is look at the density of the glass. And now to explain what density, exactly what density is. Matter varies in its mass. And something's extremely heavy, where the same volume of something else is quite light. So for example, a handful of lead is very heavy, where a handful of wood is much lighter. For the same volume, they have entirely different weights. Now, that is a reflection of the fact that the mass of the lead is much greater than the mass of the wood. The amount of atomic particles, in actual fact, in the lead is much greater. And the lead has much more mass. Now, an easy way for us to measure mass is to weigh something. It's not strictly speaking, if you talk to a physicist, they'll have said weight does not equal mass. No, it doesn't. But for all our practical purposes, weighing something gives us an indication of its mass. The reason why mass and weight are different is that the same mass of substance can weigh different amounts depending on how strong the force of gravity is that is operating on it. Weight is a measurement of an interaction between mass and gravity. We don't have to worry about that. We're just going to, for our purposes, assume that we can measure the mass by weighing a substance. So the weight of a substance, that's fine, but how do we relate the one substance to another? Because, for example, I may have a big lump of lead and I may have a small lump of aluminium. Well, the small lump of aluminium weighs very much less than the large lump of lead. But how do I relate the two? Because one, the size is different to the other, and second of all, their mass is different. How can I relate these two substances together? Well, what I can do is I can measure the amount of mass in a set volume for each. And that is what density is. Density is the amount of mass per unit volume, and we use a special unit of volume. And that is, we rate it against 1 cubic centimeter of water at 4 degrees Celsius. And that equals 1 gram. 1 cubic centimeter of water at 4 degrees Celsius weighs 1 gram. So this is what we're going to do. We're going to weigh our substance, and then we're going to weigh its volume. And then we're going to ask the question, how much does that volume of water at 4 degrees Celsius weigh? And we're going to look at the two, we're going to put the two together in a little formula, and we're going to end up with a mass per unit volume, and that is going to be in milligrams or some weight per volume, and the standard is grams per milliliter. So think about it this way. We say lead, right? Let's say we've got 1 cubic centimeter of lead, right? And it weighs a certain amount. If we take 1 cubic centimeter of aluminum, I'm sorry, I'm saying it the wrong way, aluminum, it's going to weigh far less. The same volume of aluminum weighs far less than the volume of lead. Therefore, the density of lead is much greater than the density of aluminum. And to standardize them, we relate it to the amount of water that it would displace. And we say, how much would that water weigh? Because we know 1 cubic centimeter of water, 4 degrees Celsius, is 1 gram. We end up with a measure of the amount of mass, grams per milliliter of volume. And if we wanted to do a little experiment, here's what we could do. Properly, we would do this experiment by using water at 4 degrees Celsius. It's not absolutely necessary for our purposes, but here we go. So we're going to measure the density of a solid. The first thing what we're going to do is we are going to measure its weight, its mass. We're forgetting for the moment that mass and weight aren't exactly the same. We're just going to say that they're the same for the time being. So let's say we weigh it, and it weighs 75 grams. Okay. Now we're going to measure its volume. And the reason we're interested in its volume is because we would like to know how much water at 4 degrees Celsius would it displace. So here we go. How do we do that? Well, it's very easy. Here we've got our lump. It's an irregular shape, not easy to measure its volume accurately. But what we can do is we can drop it into a known volume of cold water. And here it goes. It goes into this little test tube. We start off, it's 40 milliliters. We drop it in to the test tube and it displaces 10 milliliters of water at 4 degrees Celsius. Well, if 1 milliliter, 1 cubic centimeter, by the way, is 1 milliliter. 1 cc, cubic centimeter, is the same as a milliliter. So 40 cubic centimeters, here it starts off at 40 cubic centimeters, 40 milliliters. It displaces 10. So what is the weight there? What is 10 cubic centimeters of water at 4 degrees Celsius weigh? It weighs 10 grams, right? So our weight was 75, that's our substance. It displaces 10 grams of water, 10 cc's, 10 milliliters of water. 75 grams over 10 milliliters is 7.5 grams per milliliter. 7.5 grams per milliliter is the density of our substance there. And if, let's just say for the moment that this is lead, if we did the same thing with some aluminum, it would weigh far less, right? Let's say it weighed half. And our density would end up being correspondingly less. Density is a measure of the amount of mass in a set volume. And the set volume is related to 1 cc of water, 1 milliliter of water at 4 degrees Celsius. 7.5 grams per milliliter, the substance, that is its density. We can do the same with glass. And the advantage is that if we have a big sheet of glass, it is related to a volume. So it doesn't matter, the whole sheet of glass has the same density as a small fragment of glass. And if I measure the density of a small fragment of glass, it's going to be the same as all of the rest of the glass. It gives us one characteristic that we might be able to link between a question and a standard. The second thing that we're going to look at with glass is it's called the refractive index. Now, I'm going to miss out a whole lot of the physics of light and everything. You're just going to have to believe me about some things. First of all, light, when it travels through air, when it travels through a medium which is not very dense, like air, it travels faster. When it travels through something dense like glass, it travels slower. And there's a critical thing that happens when light moves from air to glass or from glass out to the air. And that is that this change in velocity of the light causes the light ray to bend. And that bending is called the refraction of light. So glass refracts light. It bends the light waves as light enters it. And the amount that it bends the light varies from one type of glass to another. It varies from one substance to another in actual fact, but it will vary between different kinds of glass as well. So the amount that it bends light is called the refractive index. And the refractive index can serve as well to characterize a piece of glass. So here we have two things. We have the density of the glass, that's one thing, and we have the refractive index. We've got at least two characters of glass, which might allow us to start to associate a glass fragment with a standard, a source, a possible source of glass. So this is what I mean by the light actually bending. So let's just say here we have a relatively dense medium, it's water, and we have an object sitting in the water. If you're looking and you can see that ball, you're seeing the ball because light has struck it and has been reflected off it and is coming out and is going to end up entering your eye to form an image. But here's the thing, here's a ball in reality. It's on the bottom. So let's follow the light rays as we've got a source of light and it's bounced off and it's on its way to your eye to make the image. And here it moves here. Here go the light rays here. But when they leave the water, they change velocity. In fact, they speed up as they come out. And that speeding up causes them to bend, to refract. They don't come out straight like this. They bend and enter your eye to form an image. But your eye doesn't understand this. Your brain doesn't work like that. Your brain doesn't compute like that. We compute an image as if the light rays were always straight. So here come the actual light rays coming out of the water. They bend, go into your eye, but they come out at an angle. But your eye sees in straight lines. So what happens? The eye sees the ball as being here, as being suspended, if you like, suspended, excepting don't forget that you'll be seeing the bottom there as well. This is why it's very difficult for us to tell the depth of water, of a pool of water or a swimming pool or whatever. It's very, very difficult to tell what the depth is by looking at the bottom, because you see the bottom as being much shallower because the light rays are refracted. So water has a certain refractive index, so does glass. Now think that if I shone light onto the surface of the water, if I shone light onto the surface of the water, it would also bend as it entered the water. Same with glass. As light enters, it is refracted. And as it leaves, it is again refracted. The amount of refraction that takes place at the interface between the air and the glass, that is the refractive index of the glass. And now we have these two characteristics. Different pieces of glass may have different refractive indices. Different pieces of glass may have different densities. The combination of the two, refractive index and density, begins to give us something of a character to look at, to be able to affect a comparison. But realize that this is class comparison. There are many pieces of glass which have the same refractive index and which have the same density, because that is determined by the composition of the glass, and that is determined by the manufacturer. They keep careful records of refractive index and density. It's one of the properties the glass manufacturers watch very carefully. But nonetheless, there are many pieces of glass which will share. There are many pieces of glass with different refractive indices and densities, but there are many pieces of glass which share the same refractive index and density. Nonetheless, very important characters for us to measure. So let's just think where some of these properties actually arise from. And I will describe this as being a feature of very largely of the manufacture of the glass. But glass in general actually has a relatively simple composition. The basis for glass is a compound called silicon oxide. It's actually usually a silicon dioxide, which is sand. But in order to manufacture ordinary sand, garden sand, whatever, is contaminated with all sorts of other substances. To manufacture glass, they use a very high quality sand, silica sand, and it's often mined or extracted from rivers where it's clean, etc. And that is melted, and it's melted to then be cast into the glass form, whatever glass form we want. But on its own, that has certain things about it which make it not that desirable. It's not very, just on its own, silicon oxide is not very strong. So it is strengthened usually by adding various substances to it. And there is especially various metals and metal ions and metal oxides and things are mixed to alter the properties of glass. Now, I should explain that glass is actually a very peculiar substance. Usually a solid, something that's solid at room temperature, for example, usually has either crystalline structure where the atoms are very tightly tied together in a matrix with a regular pattern, or else some way have bonds between them to establish long molecules, etc., etc. Glass is much more like a liquid in that it has no real internal structure. It is not crystalline. It looks, its atoms, if you could see them, would look much more like a liquid in that they are randomly distributed and their bonds are randomly distributed. So it is referred to as being an amorphous structure, an amorphous solid rather. When you break it, it doesn't break along crystalline lines. If we wanted to break in a certain way, we have to introduce some stresses into the glass, as I'll show you in a minute. In order to strengthen glass and impart certain properties, when it's melted, they add, the most common additives are sodium carbonate. Sodium is a metal, but sodium carbonate is a salt. And that actually lowers its melting point, makes it much easier to deal with in manufacturing process. Then we usually also add calcium carbonate. And the reason for that is it makes the surface of the glass much more durable. Glass will dissolve in water, especially acidic water, very, very slowly. But what happens is that the surface of the glass begins to cloud and pit and become opaque, which is usually not desirable. So calcium carbonate, lime, is added, and that improves the durability of the glass. And that is the commonest. Glass, which is mixed with sodium carbonate and with lime, is called soda lime glass. And most of our glass, window glass, glass, bottle glass, glasses that you drink out of, most of these are soda lime glasses. Then other metals can be added. For instance, boron oxide makes a very, very high temperature resistant glass. And that is typical of glass like Pyrex glass, which you use in the oven. But it also makes the glass very, very tough. And that's often used in car headlights. Glass can also be colored by adding various oxides to it. So depending on what the manufacturer wants to do, a particular recipe of glass may have its own composition. Well, this gives us another way of starting to characterize glass. If we can look at what metal ions does it have in what concentration, that may also give us a way of being able to identify a particular piece of glass. So just show you how glass is made. It's actually an amazing process. Glass, the raw materials, whatever they are melted in a furnace. It has a very high melting point. And it's melted to a very liquid consistency. And it is passed through a furnace which gradually cools the glass sufficiently, it is melted in such a way that it naturally flows out in a sheet form, which when it's sufficiently cool, it is still essentially liquid, but it can be manipulated. It can be rolled and it can be drawn out. And that is what happens. And it is then floated, believe it or not, on a bed of molten metal. It's usually tin, molten tin. And because it's floated on tin like that, it's called float glass. That is the main way that window glass is manufactured. It is, as it passes along here, it actually, although it's sitting on this bed of molten metal, it starts off here very, very hot, much hotter than it ends up here. And this gradual cooling is called annealing. And the annealing process leads to the glass being harder and tougher. And it is still malleable. It can still be molded. And it's drawn out of this float chamber and is then rolled to a standard width. And once it's in that standard width, it is allowed to gradually solidify to confirm the annealing, and is then cut up into whatever. Here's one of the machines here, floating the glass out. But remember, what is critical for a forensic examiner is what the manufacturer is putting in here. What is going in to make up this glass? Because individual batches of glass may have their own character. They may produce a huge amount of glass with that character, but nonetheless, different batches may have different character. Careful record is kept by the manufacturers of what they put in. And there is a possibility that we could go back and find out for a particular batch of glass. When, for example, we could analyze a piece of glass, find out how big, when was that batch made? How big was the batch? How many manufacturers, how many retailers received glass of that type, etc., etc. Okay, so our ordinary window glass, you know, when you break a window, it shatters into large polygonal pieces with very sharp edges and very often very sharp points, extremely dangerous. If you go accidentally put your hand through a window or you fall through a window, it can do an enormous amount of damage because of the razor sharp edges that are produced. So for this reason, manufacturers develop methods of toughening glass, but also of making it much safer. In the old days, when cars were first manufactured, for example, windscreens were just ordinary glass. They were like thick window glass. It was terribly dangerous because if people went through the windscreen or if the windscreen shattered and flew in, very often people were very, very severely injured just by the windscreen. And this was one of the main reasons why this form of glass, tempered glass, was developed. And in tempered glass, what they do is when the glass is still semi-molten, it's being rolled out, they cool the outsides very quickly. And this causes stress points to run across the glass. You can't see them, but there are stress points that run perpendicularly between the surfaces of the glass. And if you shatter that glass, this is how it shatters. It shatters into these small pieces, and the edges are at right angles to one another. They don't form these pointed edges with razor sharp breaks. And this is much, much safer. It still can do damage, but it's unlikely to slash arteries or anything like that. You've probably seen windscreens which have been broken, and you know they break into a shower of these very small pieces of glass. The other kind of glass was developed is laminated glass. And this was also for safety reasons. In the old days, glass doors and things like that were ordinary thick window glass. People walked through them and could be killed by the results, the shattered glass. Instead, this is laminated glass. And laminated glass is typical for doors, for many windows, and also, by the way, for bulletproof glass, which I'll just mention at the end. So laminated glass is sheets of glass which are with plastic sandwiched between them, and the glass is adhesive to the plastic. It's all one sheet. But if you break the glass, this is how it breaks. It doesn't break and fall out. It stays as a coherent whole. And it also tends to shatter in very small pieces like this. So it's very difficult to get, very tough. You can't go through it the way you could go through a window pane or something like that. Now, bulletproof glass is just like this. It's the same principle, except you have thick layers of glass, several thick layers of glass, and several layers of plastic. And it drastically slows the velocity of a bullet passing through. It may not stop it entirely, but if a bullet should make its way through a piece of bulletproof glass, the velocity of the bullet is so slow that it does only do minimal damage if it gets through at all. So this is this is a typical ordinary window glass. This is tempered glass, shattering into these very small, far less harmful pieces. And this is laminated glass, which stays as a coherent whole even when it's been broken. So here's the real problem for us. If you're just looking at a piece of glass, there is actually very little that would give it individual character. Very large amounts of particular types and recipes of glass are manufactured and are widely distributed. And when glass is recovered from a crime scene and then we try to make an association, give it evidentiary value, there's actually not a lot of character to the glass which can be used. There have been several cases. I think one of the videos I've given you has one instance, for example, where a suspect subsequently proved to be guilty, but a suspect was examined, his clothes were examined, and glass fragments were found. And at the scene of a crime, glass had been shattered, and they were very determined to make an association between the two, and it came back. The two pieces of glass from the scene and glass found in his clothing were completely unrelated to one another. There are many reasons why somebody might have glass on them, and we have just the fact the glass was broken at a crime scene and glass was found on a suspect does not tie the two together. And it is, in fact, quite difficult to do so. So the first thing that an investigator is going to do is they're going to try and determine the density. So doing it the way we talked about initially, it's a good experimental way to demonstrate what density is, but it's not a very practical way of immersing things into water and trying to measure the volume for one important reason. And that is the fragment of glass whose density you're trying to determine may be very, very small. It may be extremely difficult to determine the volume, for example, of that piece of glass, to determine it accurately. So instead, what we'll do is we'll make use of an important property of density. And that is, if I take a substance and I try to immerse it in something with a much greater density, a liquid with much greater density, then the object will float. If I try to immerse it in a liquid whose density is much lower, it will sink. Simple. Okay, if we take, you think of water, if we float wood on water, it floats. Why? Because the density of wood is much, much less than that of water. It floats. Try to float lead on water. Try to float the same volume of lead on water. No, it's not going to. It's going to sink because the density of lead is much greater than water. So here's a trick for us. Why don't we take a liquid whose density we can vary? And that is easily done, because you can vary the density of a liquid, for example, by heating it. That's one way. Or we could add solvents to it gradually and lower its density. So we start off with a very dense liquid, and we're going to add solvents to it, and we're going to lower the density, lower it. So this is exactly what you do. This is how density can be determined. It is usually immersed in a liquid. The liquid will vary, but the density is changed. So we're going to take our piece of glass, and we're going to put it in, and we're going to watch what happens. So probably the glass is going to sink. The density of the liquid is then changed in a scientific manner by adding solvent, known volumes of solvent to it. The density decreases and decreases and decreases until the glass fragment begins to float. And at that point, where it's starting to float, the density of the liquid and the density of the glass are exactly the same. And we can determine the density of the liquid because we know its properties. We know what its property. We know that at such and such a point where with so much solvent, so much liquid, the density per milliliter is X. That's easily determined experimentally. We don't have to know the volume of our piece of glass, no matter how small it is. If it's floating, if it's just lifted and is floating in equilibrium with the liquid, the density of the glass and the density of the liquid are the same. So that's the flotation method to determine density. Now, what about the refractive index? Well, this is the standard method for determining refractive index. And again, what we're going to do is we're going to immerse our piece of glass, and we're going to immerse in a liquid. But this time we're going to watch, we're assuming we're going to take, like, if the glass is not already very small, we can take small fragments of it. We're going to do this under a microscope, and we're going to watch. We're going to drop the glass fragments into a liquid. It's actually an oil. And it's on a special microscope where the oil can be heated. And as the oil is heated, its density is going to drop, and its refractive index is going to change, because refractive index is in fact related to density. The denser something is, the slower light waves pass through it. So when you look through the microscope, you see something particular. We're going to take our glass fragment, we're going to immerse it into oil, whose density and whose refractive index is radically different to that of the glass. And we see this, it's called a Becker line. And it's a kind of a halo around the glass fragment. Here's the microscope. And the microscope has a stage which can be heated. So it's going to heat up, and this measures the temperature very, very accurately. This is filled with oil, and we immerse our glass fragment in the oil. And this is what we see. As we're looking through the microscope, you see these bright lines here and these dark lines here. These are the Becker lines around the glass fragment. And the reason that they're there is because the refractive index of the oil is so different to that of the glass. It causes this optical illusion of a line around the glass. So now we're going to start heating. This is room temperature. We're going to start heating the oil. And we heat up the oil. And as we heat the oil and the density, the refractive index rather, of the glass falls, as it gets less and less, these lines begin to fade. Here they still, this is 68 degrees Celsius. They are still visible here. But when we get to close to 100 degrees Celsius, boiling point of water, but not of oil, get it really, really a low refractive index, the glass disappears. And at the point at which the glass disappears, you make a note of the temperature, and we know the properties of the oil. That is standard. They can go look it up on the table. What is the refractive index of this oil? You could look up what its density is too, but you could look up what the refractive index of that oil is at this particular temperature. And if the glass fragments have disappeared, the refractive index is the same. And the other thing to note is you can do this with very small fragments of glass. Very, very small fragments of glass. You don't have to shine light through them or anything. Here it's all done for you under the microscope. Fragments this small are almost like sand, and they can be recovered easily, for example, from clothing or something like that. Okay, so you'll realize that there are a limited number of characteristics to distinguish glass, but nonetheless, the FBI maintains a database, especially of densities of glass, and this is all here shown here. These are the number of manufactured glass samples that they have tested, which have a particular refractive index. You can see this axis here is the refractive indices. This is purely number. So most, you'll see that this is the most common there, but there's a huge range of refractive indices for different glass samples. And a forensic expert who has determined a refractive index for a piece of glass, for example, can come to this database and know, if they know, for example, that their refractive index is this here, I don't know what it is, 1.51 or whatever, this here, then at least the FBI would be able to tell them, well, here is a list of glass samples that we have tested which had that same refractive index, and here are their manufacturers, and here are the batch numbers, etc., and the dates they were manufactured, and all the rest of it. It at least gives some chance of establishing class character for a glass fragment recovered from a scene. The other hope in forensic science of glass is that, in actual fact, in this process, I'm going to go all the way back here. In this process here, during the manufacture of glass, there are incidental inclusions of various elements, which are not intentional by the manufacturer. It's just they come in on the raw materials, for example. And these are traces of different things which become included in the glass. And they're often included just maybe for one batch or whatever of the glass manufacture. If you're getting your sand, your glass sand from different sources, for example, those different sources may be contaminated with different elements, which will then be included. And this gives the chance, at least, of developing some sort of identity for glass, which is much more individual, at least to tie glass to a particular batch of production or something like that. And this can be analyzed by various means. The easiest in terms of laboratory practice is to use a laser system, which will give a composition of elements within the glass. But it can also be done, for example, with scanning electron microscopy. So the other thing that may convey some information for us is that obviously glass cracks, glass shatters. But because it's an amorphous solid, the shattering is random. Glass is not a crystalline substance. In tempered glass, we do introduce an artificial kind of crystallization. But in normal window glass, that kind of glass, the shattering is actually relatively random, but there is a pattern to the cracking, which may be informative. So if we have a window glass, for example, and something penetrates that glass and shatters it, it produces cracks with a distinct character. And there are two types. There's one, the one lot is called the radial cracks. And those are the straighter cracks that run out from the center, from the point of impact of the glass. And then there are concentric cracks, the circular cracks, which run around and around and around. So here in this picture here, these would be radial cracks here. And then these are the concentric cracks running around. And the second thing is that when the projectile, whatever it is, bullet or stone or whatever, if it goes right through the glass, it will leave a larger hole on the exit than on the entry. So these two things, the fact that these cracks run in particular directions, and the fact that the exit hole is larger, may enable us to determine a direction that a bullet, for example, came through a window. So when cracks develop, they develop because glass is stressed beyond a point where it can be mechanically maintained. Glass is actually quite flexible. You can actually bend glass quite a lot. But if you bend it too much, you're going to introduce stresses into the glass, which it cannot sustain, and the glass will break, it will separate. So the very first, when something goes through a window pane, here's the window pane entire, here's something going through. When the projectile first goes through, the first cracks that develop are the radial cracks. And then the second lot of cracks are the concentric cracks. It's difficult to conceive here, but here's a radial crack developing, and you can imagine them going in all sorts of directions, which is difficult for us to show in this kind of diagram. So these are going in straight lines out from the center there. These are the concentric cracks developing here. And they will obviously, they've only shown one ring, but there may be many of them. Okay. So when you analyze glass, even if it's in small fragments, if you look at it under special lighting, under the microscope, under polarizing light, you can actually see the stress marks which were induced in the glass. Glass is an amorphous solid. And when you do something violent to it, like throw something through it, you introduce stress into it, and that stress is recorded actually in the atoms of the glass. So you look at it under special lighting, and this is what it looks like. Here's a fragment of glass which has been broken. And when you look at the stress lines, see how they run. Here they're running at about 180 degrees to the surface of the glass, but they bend over, they curve over, and here they're running at 90 degrees. They're running perpendicular. The perpendicular side here, that is the exit side. For the radial cracks. Okay, for the radial cracks, that's the exit side there. For concentric cracks, look at the concentric crack. Now you can see it here. There, you see how it's broken in a wedge that facing that way. Look at the concentric cracks, they're broken here. In the concentric cracks, the stress lines run like that. So if we examine fragments of, even if the window is completely shattered, we can't tell. We can take fragments of glass and we can see the direction in which they were broken. Oh, there's a little acronym for it. Radial cracks form a right angle on the reverse side of the force. So in actual fact, for the concentric cracks, they are resulting from bending. Their force is that way. The force that results in the concentric cracks is coming this way. The force that produces the radial crack is going that way. And so here, the stress lines bend this way. In this case, they bend that way, like that. So, and this is the exit hole again. And the exit hole may tell you not only from which side the projectile came, it may also contain some information about direction. So what if several impacts are made on glass? What if we've got, for example, several bullets get fired through a window? Each of them is going to possess a set of cracks, but contained in those cracks, actually, we can see the order in which the window was cracked, because a crack will not run through another crack. A crack will terminate at a crack. So have a look what I mean by that. What's the order of, here are 3 cracks resulting from 3 different events, 3 different impacts, okay? What is the order? Well, it has to be that this one was first, because look here, we've got another crack coming here, but it's terminated there. So what you do is you look, where does the crack terminate? That's the end. The crack was running in that direction. If it terminated here, that had to be there first. So that crack was second there. This was first, that's second. And this one here is third. And if we trace these back, for instance, to bullet holes, then we'd be able to say, okay, that bullet came first, that one came second, that one came third. The fracture always terminates at another existing line of fracture. It can't go beyond it. So in real terms, have a look here and try and decide which was the first bullet hole that went through. Which hole was created first? Well, have a look here. Have a look at this crack here and have a look at this crack here. These radial cracks, that one there, and that one, this one terminates there. That's the end there, right? So this had to be there first. For this to run this direction and end there, this one had to be there first. This bullet hole was made first. This was made second. Now, it is possible that if glass, especially from a window, from an ordinary window, if it shatters, it is possible that glass could be pieced together and some story could be told, especially if glass fragment is recovered, say from a suspect or from a suspect's vehicle or something like that. And if those could be pieced together, it is very strong individual evidence, but this is extremely rare. Nonetheless, if the possibility exists that such a matching could be done, then all of these glass fragments need to be collected from the window in question and need to be kept in such a way, for example, that they do not butt up against one another and chip and damage one another. They must be collected individually, packaged carefully, probably wrapped in tissue paper or something like that, in the hopes that an individual matching like this could be done. But I have to emphasize, this is extremely rare. Nonetheless, the evidence still needs to be collected if there is any possibility that such a matching could be made. The same thing, of course, cannot be said for tempered glass, which shatters into a cloud of pieces, which would be impossible to piece together. But instead, in that instance, where it's obviously not going to be possible to do an individual piecing together, nonetheless, glass fragments need to be collected carefully so that they can be analyzed for density and for refractive index at the very least. In addition, glass fragments need to be very carefully examined because they often have fingerprints on them, and they may have blood and other tissue evidence as well. So glass fragments need to be very carefully examined at the scene of a crime or wherever they are recovered, and they're examined for all of these things: blood, fingerprints, tissue, all of those sorts of things. So the packaging has to be done. Glass is the bane of an evidentiary technician's life because it has to be, there's often so much of it, and it has to be carefully collected and packaged so that no damage occurs. And it's I said right at the beginning, the glass is a frustrating piece of physical evidence because it often entails a lot of work for no great benefit. But in some cases, it has proved to be critical in a case. Okay, so that is that for today. I hope you all have a good spring break, and stay safe, wear your masks, please. Stay socially distanced, despite the fact that it is spring break. The epidemic is still with us, very, very much with us, and you do still need to be careful. Please, I want to have you all back safe and sound when the spring break is over, and I'll see you then.